Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Electrical Properties of Thin Films from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. Firstly, in this module, the Hall measurements of the thin film samples are discussed. Secondly, electrical resistivity measurement using the van der Pol method is explained. Third, contact methods for resistivity studies are discussed. Next, the concept of current voltage and dielectric studies for thin films characterization are discussed. Finally, capacitance voltage measurement for thin film samples is explained. The results from the extensive study of the properties like conductivity, temperature dependence, and thermal stability has led to the application of thin films as resistors, interconnections, and contacts. Such properties of thin films are highly structure dependent. The conductivity of thin films vary with the orientation of the normal to the surface with respect to the crystallographic axis, even for the materials having cubic symmetry, such as silicon, for example. Hence, the study of electrical and dielectric behavior of thin films helps to gain insight into the structural properties of films, which is important for practical applications. The characteristics of thin films and different aspects of the growth parameters and the growth mechanism can be understood well by the electrical characterization of the films. Several techniques are being exploited for these studies. In this module, we will study briefly about some of them, such as Hall measurements, contact method for resistivity studies, current voltage, and capacitance voltage studies. Let us discuss about the Hall measurements. Hall effect measurements are a valuable tool for characterization of thin films. Hall effect is observed on applying a combination of magnetic field across a sample and current along the length of the sample. This results in an electric current in a direction perpendicular to both the applied magnetic field and the current, which in turn produces a transverse voltage in its direction. The underlying principle is the Lorentz force, that is, the force on a point charge due to electromagnetic fields. The electrical properties of semiconducting samples can be studied using Hall measurements. Hall effect was discovered by Edwin Hall in 1879. When a current carrying semiconductor is kept in a magnetic field, the charge carriers of the semiconductor experience a force in a direction which is perpendicular to both the magnetic field and the current as shown in figure 1. At equilibrium, a voltage appears at the semiconductor edges. This voltage is known as the Hall voltage, which is generated due to the collection of charges at different ends, which are perpendicular to the direction of applied magnetic field and current. The Hall coefficient is defined as the ratio of induced electric field to the product of current density and the applied magnetic field. It signifies the characteristics of the semiconducting material as its polarity depends upon the type of conduction and magnitude and depends on the and depends upon the carrier density and properties of the charge carriers that constitute the current. In the case of semiconductors, the charge carriers are generally both electrons and holes that may be present in different concentrations and have different mobilities. The Hall coefficient for moderate magnetic fields is given as RH is equal to minus n into mu e square plus p into mu h square divided by e into square of within the brackets n times mu e plus p times mu h brackets close, where RH is the Hall coefficient, n is the electron concentration, p is the hole concentration, and mu e is the electron mobility, and mu h is the hole mobility. Polarity of Hall coefficient, that is sign of RH, gives an indication of the type of majority charge carrier in a semiconductor. That is, if RH is positive, the material shows p-type conductivity. Otherwise, if RH is negative, the material possesses n-type conductivity, having electrons as the majority charge carriers. To measure the electrical resistivity of the sample accurately, Van der Pol method is used for semiconductors. The objective of the resistivity measurement is to determine the sheet resistance Rs. Van der Pol demonstrated that there are actually two characteristic resistances, Ra and Rb, associated with the corresponding terminals as shown in figure 2. Ra and Rb are related to the sheet resistance Rs through the Van der Pol equation, given as exponential of minus pi Ra by Rs plus exponential of minus pi Rb by Rs equals 1, which can be solved numerically to obtain Rs. Bulk resistivity Y can be calculated using the equation rho equals Rs into d, where d is the thickness of the thin film under investigation. To obtain the two characteristic resistances, one applies a DC current I into contact 1 and out of contact 2 and measures the voltage V43 from contact 4 to contact 3. Next, one applies the current I into contact 2 and out of contact 3 while measuring the voltage V14 from contact 1 to contact 4. Ra and Rb are then given by Ra equals V43 by I12, Rb equals V14 by I23. Let us now study the contact methods for resistivity studies. Measurement of resistivity is commonly studied by the contact methods that include two-point probe, four-point probe, and the spreading resistance. The simplest and easy to use among these is the two-point probe method. It is useful for thin films having very high resistivity. In this technique, a constant voltage V is applied between two probes with a fixed position and separated by a distance d in centimeter, and the resulting current passing through the sample of known dimensions is measured with the suitable current meter. For a sample of uniform dimensions, the resistivity is given by rho equals A into V divided by I into D with the units of ohm centimeter, where A is the cross-sectional area of the sample. For semiconducting thin films, the resistivity decreases with the increase in temperature. The thermal activation energy EA can be calculated using the following equation, which is rho equals rho naught into exponential of minus EA by kT, where K is the Boltzmann constant, capital T is the temperature, and rho naught is the resistivity of the sample at 0 Kelvin. The slope of the plot between log of rho versus 1 by T gives the activation energy. We next discuss the current voltage studies or IV studies. Electrical properties of the metal oxide thin films can be studied in the metal semiconductor metal configuration, which is also known as MSM configuration as shown in figure 3. The schematic diagram of a three-terminal sample cell that is commonly used for electrical characterization of thin films is also shown in figure 4. It may be seen that the outer jacket of the sample cell is made up of a thick brass block to shield it from external electrical disturbances. To ensure a good connectivity of the copper rods, that is sample cell, with the top metal dots, which is the sample, pressure contacts are required, which are provided with a low tension spring on the rod so that the sample always remains in a stress-free condition and the electrical connections are made properly with the BNC cable. The bottom electrode of the sample can be connected with the copper plate using silver conducting paste. DC conductivity of the thin films may be measured with the help of a Keithley 4200 SCS electrically connected with sample cell. The value of DC conductivity is estimated at a fixed DC bias voltage selected from the ohmic region of the IV graph. The DC conductivity is calculated using the relation sigma DC equals 1 by V into within the brackets T divided by A with the units of ohm inverse centimeter inverse. Here V is the applied voltage, I is the current flowing through the sample, and A is the area of cross section of sample, and small t is the thickness of the film. We next take up the dielectric studies. The dielectric response of solids provides information about the orientational adjustment of dipoles with fractional losses and translational adjustment of mobile charges present in dielectric medium in response to an applied AC electric field. When a dielectric is subjected to an AC field, the polarization P varies periodically with time, and it may lag behind in phase with the applied electric field by an angle delta. The dielectric response of a material is usually explained in terms of a complex dielectric permittivity, which is E star of omega given by E star of omega equals E prime of omega plus J times E double prime of omega, where E prime of omega is the dielectric constant, E double prime of omega is the dielectric loss, and omega equals 2 pi f is the periodic frequency of the applied field. The tangent of the loss angle delta, that is tan of delta, is given as tan delta equals epsilon double prime of omega divided by epsilon prime of omega. The dipole polarization arises from the permanent dipoles in a medium, which is random in the absence of electric field, and it orients in the direction of applied field. The polarization decays in time on removing the field and is given by P equals P naught into exponential of minus T divided by tau, where tau is the relaxation time and P naught is the initial maximum polarization. The Debye theory, which was given by Debye in 1945, expressed a relationship between the dielectric constant, which is epsilon prime of omega, and the loss, which is epsilon double prime of omega, in terms of relaxation time and frequency. So epsilon prime of omega is equal to epsilon naught minus E double dot divided by 1 plus omega square tau square plus E double dot. Epsilon double prime of omega is equal to omega into tau into, within the brackets, epsilon naught minus epsilon double dot divided by 1 plus omega square tau square. Here, epsilon double dot is the dielectric constant at infinite frequency, where the contribution from only ionic and electronic polarization are dominant. And epsilon naught is the low frequency limiting dielectric constant having contribution from dipolar polarization as well. Later on, Froelich showed that in solids, if an electron or ion has two equilibrium positions, the occupancy probability in one of the wells will increase under the applied electric field, which distorts the potential well, thereby giving a dipole in the presence of the field, and in addition to ionic and electronic polarization, will have a polarization which decays exponentially to its equilibrium value on removal of the field, just like dipole polarization, and one can get the expression for epsilon prime of omega and loss epsilon double prime of omega exactly same as given by Debye in 1945. The equations for epsilon prime of omega and epsilon double prime of omega, given as equations 11 and 12, represent a well-defined single relaxation time tau. However, in a real material, there are random distribution of potential well and relaxation time. In case of very wide distribution of relaxation time, the peak in epsilon double prime of omega, that is dielectric loss, which was represented by equation 5, loses its significance. And it is completely masked by almost frequency independent dielectric loss. In such a situation, it is customary to represent the dielectric data in terms of epsilon prime of omega and AC conductivity sigma AC in low mobility, or I can say insulating materials. The AC conductivity sigma AC can be expressed as sigma AC is equal to capital A into omega raised to power S, where capital A and S are the parameters. Such a frequency dependence in AC conductivity is observed in a wide variety of low mobility, amorphous, and crystalline materials, including single crystals. In the presence of electrode polarization and barriers in the film, and replacing conventional dipolar polarization by the polarization due to hopping of charge carriers, that is capital P hop, with wide distribution of relaxation times, the total polarizability capital P of the dielectric is capital P is equal to PE plus PI plus P hop plus PSC, where PE, PI, and PSC are the electronic, ionic, and space charge polarization per unit volume respectively. Their relative magnitude depends on the materials and systems. The variation of four polarizabilities with frequency is shown in figure 5. In general, PSC, which is the space charge polarization per unit volume, can arise due to inhomogeneities in the bulk of the sample, which is also known as Maxwell-Wagner polarization, or electro-depolarization, and gives a dielectric dispersion very similar to the dipolar relaxation, especially at low frequencies and relatively high DC conductivity, or we can say at high temperatures. We will now study the capacitance voltage profiling of thin films. The capacitance voltage measurements, which is CV measurements, is a widely used technique for characterizing thin film devices. In CV measurements, capacitance of a sample is measured by varying the applied voltage. The CV measurement systems are conventionally done in a fixture which is placed inside an enclosure with no light inlet to prevent errors due to photo-generated currents in the sample. MIS, which stands for Metal Insulator Semiconductor. MIS capacitance is widely used for studying the electrical properties of thin films. These measurements reveal a lot of information about interface charges, ion transport through the sample, and its impurity profile. The charge storage capacity or the capacitance can be calculated as C equals epsilon naught into epsilon r into A divided by D, where B is the thickness of films. Capital A is the area of electrode which is used for measurements. Epsilon naught is the permittivity of free space, and epsilon r is the relative permittivity of the material. We will now discuss the various configurations for CV measurements. Capacitance voltage measurements or CV measurements can be done in the following two different configurations. First one is the quasi-static configuration. This configuration corresponds to the equilibrium condition. The CV measurements in this configuration are made by sweeping bias voltage applied across the sample. The displacement current is measured as a function of time. The quasi-static measurements are useful only if the film is not too leaky, as the leakage current will lead to conduction current that adds to the displacement current and results in inaccurate measurements. The capacitance is measured by directly integrating the charging current over time. Another configuration is the high frequency configuration. The CV measurements can also be made by a small sinusoidally oscillating AC signal over the sweep voltage and measuring the resulting impedance directly as a function of bias voltage. A high precision impedance meter is required for the high frequency configuration. So students, let us now summarize what we have learned in this module. In this module, the hard measurements of thin film samples were discussed. Secondly, electrical resistivity measurement using the Van der Pol method was explained. Third, contact methods for resistivity studies are discussed. Next, the concept of current voltage and dielectric studies for thin film characterization were discussed. Finally, the capacitance voltage measurement for thin film samples was explained. Thank you students for your attention.